is the estimation of parameters in linear dynamic models as we've kind of been warming up to go there. And then I'll go through an example where we do this and also look at analysis of the residuals from a model, just so that you have some examples to use in the future. So remember from last lecture that we will need to first identify which structure of the model that we want, and we will take the starting point in looking at the autoregressive autocorrelation function and partial autocorrelation function and see if it goes very fast to zero for one of these to say it's an AR and MA, and we also discussed if this is not the case, how to proceed, assuming that it may be an ARMA model at first, and then taking it from there. Okay, so given a structure, then we have to find appropriate values. And the book contains quite a list of such things based on moments, as in the mean and the variance structures, also some d-squares methods, prediction error estimates, conditioned and unconditioned, we'll get back to that, and finally also maximum likelihood, which is again conditioned and unconditioned. So these are the different things that we're going to look at, different methods or terms that we're going to apply. There's also some of these coinciding for most of the methods that we're going to use, so we're not going to go that complicated after all. Okay, so let's just start with an example. We're looking at this time series here, and what we said is that from looking at the autocorrelation function and partial autocorrelation function, we found that an AR2 model is appropriate, and we just have to pick appropriate values for A1 and A2. So first of all, here I used one definition of the sign of the parameters from the book. Usually it uses the phi to be positive on the left hand side, so that means when you move it to the right hand side, it'll become negative. This is one thing to be aware of, which software you're using and what is the definition there. In the ARIMA function that we'll use later, this is the definition that we will actually be using underneath the hood. Okay, so what do we have? We have some observations. For each observation, there is a one-step prediction error, epsilon t plus 1 given t. We have the prediction, and then we have the observed value as this. We can write it up as for each of them. You should be aware of one thing. The first residual that we have is a time 3 in this case, because we need the first two observations to make a prediction for the third one. This we can write in the usual vector matrix vector form, leaving a vector of epsilon here, and the solution for this is the usual least square estimator, which we'll get to here. So we have the theta hat is equal to x transpose x inverse x transpose y, with this particular design matrix here where you have a column of minus the observations time shifted 1 lag and yet another lag. So the number of rows here is n minus 2. And asymptotically, we have the usual variance estimate of theta, and we call it the d-square estimator, as we've done previously for other kinds of model, but it is the same thing. But this is also a prediction error method, since we minimize the sum of squared one-step prediction errors. So we already covered, you can say, one solution, two different methods. Now, if you do not have an AR2 model but an AR3 model, what do you do? Well, all you need to do is to add an extra column here, and then you will also remove, say, you do not have y 0, so you need to also remove the first row. So you have a column, you have removed the first row here, and the first value will then be minus y3 and then minus y2 and then minus y1, going down to the same down here, except that it's n minus 3 for the last column. So everything is the same, you just add an extra column. So it's fairly easy to do for autoregressive or pure autoregressive models. As a very brief example, if we have some observations from a process, we have the length is 6. We take the last 4 observations here, define them as the observations, and then we columbine first from the second to the n minus first, and from the first to the n minus second observation in 2 columns to get this design matrix, and then we use the usual solution to get these estimates down here. Just as a very brief example. It's pretty much what we've done previously. It's just for an autoregressive model, but the estimation is the same. Now, what we also looked at is combinations of AR and MA models, so-called AMA models. So here we have a model. Notice again here that we have the phi is positive on the left-hand side. And what we'll do is we'll define a vector theta with all the parameters that are involved, phi1 to phi p, and theta1 to theta q. And then we have a vector of all observations up to time t is the bold y. So the likelihood, we discussed this earlier again, is the joint probability distribution function for all observations for the given values of theta and sigma epsilon square. And that is just the density as given here. So given the observations, what we need to do is to find the parameter values that maximize the likelihood. How do we get about that? First of all, when we look at this, this is a multivariate, an n-dimensional random variable. If we assume the epsilons are normally distributed, it's an n-dimensional Gaussian distribution or normal distribution. So it's not so nice. So let's first consider, can we actually make these things more simple? So if we look at the random variable that is yn, given that we know everything up to yn minus 1, then only epsilon n is the random component. So we look at a one-step prediction. Epsilon n is assumed to be white noise, and therefore is independent of everything that has happened in the past. So if we have this, then we also know that this random variable is independent of yn minus 1. So we can take, since they are independent, we can take the joint density and write it as a product of the individual marginal densities. One here for only the scalar yn, and the other one here for the density of the joint density of all observations up to time n minus 1. But again, this last one here can be expanded in the same way. So if we repeat these arguments here for the density of yn minus 1, what we'll get is the following down here. So we'll get all the one-step prediction here, errors, the density for those, from time p plus 1 to n. We cannot go any further back because we need the first p, where p here is the order of the AR model, in order to make the prediction. So we need to deal with this out here, you can say on its own, but typically p is much less than n, so it's a much simpler density we have to look at out here, whereas all these here are just univariate distributions. Okay, so if we do so-called conditional likelihood function, what do we have then? We condition on the first p observations. So basically what we do is that we just remove or ignore this last term out here and say now that we have the conditional density, we can do everything easier because we just have to make one-step predictions. When n is sufficiently large, well, we get very close to the exact likelihood. And of course, the smaller the sample, the larger the difference. The ARIMA function in R actually does do the exact thing as in non-conditional. But if you want to do things by hand, this is where you want to go. So the next thing is to evaluate the likelihood function. Let's just go for the conditional likelihood function. What do we need to do? Well, we have given parameter values. So what we need to look at is this random variable of the one-step prediction, and it has variance sigma epsilon square. We will, for now at least, as always in this course, assume that the process is Gaussian. So the density of yt given all the observations up to yt minus 1 for the given parameters is the density of a univariate normal distribution. And what we then have to do, if we go back one slide, is to calculate the product of all those over time, and then we get the combined likelihood down here, or the conditional likelihood function, where we have the sigma epsilon squared to the n minus p power. Again, p here is the order of the AR part, not the total number of parameters, because that's also the number of elements in the sum out here. So to maximize the likelihood, what we need to do is to maximize this, and next we can just write it. What we need to look at is to minimize the sum of squared prediction errors. If we go back one slide, we have sigma epsilon in here and we have a minus there, so we want to minimize this to maximize the exponential of that. So when we, for given sigma epsilon, that's what we want to do to find the maximum likelihood estimate of theta hat. Then we want to minimize the sum of squared errors. Well, that's the same thing as for the least square. So we are on familiar ground here. If we differentiate the likelihood from the previous slide with respect to sigma epsilon square, it can be shown that the maximum likelihood estimate of sigma epsilon square is the sum of squared prediction errors divided by n minus p, where p is again the order of the AR part. So this estimator here is asymptotically unbiased and efficient, and the covariance matrix is approximately 2 times the estimated sigma epsilon square times the inverse Hessian, which is the second order partial derivative of s of theta evaluated at the minimum. This is the usual story that we have done for the previous models as well. So not so much new here, it's just a new context. Now, if we want to find the maximum likelihood estimates using prediction errors, as in one-step predictions, we need to make these predictions. For given parameter values, we can do this, but we need to look at the epsilons out here. How do we deal with those? The easy thing is to set all the first p epsilons to be 0, actually down to p plus 1 minus q. If q is greater than p plus 1, that will be negative epsilons as well. So that means from time p and then just backwards in time, no matter how far you have to go, we'll just assume that the epsilon is 0. With that given, we can evaluate the first y hat p plus 1 given p. We have the observations here, and we know that all these out here are 0. So we just basically calculate the first part, and then from that we can calculate epsilon p plus 1. when we compare this with yp plus 1, as we do down here, then we can use that to calculate y hat p plus 2 given p plus 1, and thereby get epsilon p plus 2, and keep doing that until the end of the data set that we have. In order to find the optimal parameters, you will generally need to find, you just want to minimize the sum of the square prediction errors, and in a case like this simple model where you have an AR1 and moving average part of order 1 as well, with parameter AR is minus 0.7 and MA of 0.4, then I've evaluated the likelihood, evaluate S of theta for a range of different values and just shown you here a contour plot. And you can see that the true value is actually in here. You should be aware of one thing, that is the AR parameter here is positive, whereas if you move this to the right hand side, it will be negative. So the estimate you'll get in ARIMA would be negative. That's also why the simulation here is done with minus 0.7. But in the formulation up here, it's plus 0.7. It's just a small detail, but it's one thing to keep in mind. How R generally has positive coefficient on the right hand side, whereas we generally have it as a polynomial in B on the left hand side, and thus it will change sign when you move it to the right hand side. Okay, so that was just an overview of an example. The last method is, you can say, general moment estimates. Given a structure, what you do is that you calculate the theoretical autocorrelation or autocovariance function from the model structure, and then you calculate the sample autocorrelation or covariance function, and then you solve this pair of equations by using the lowest number of lags that are necessary. It's generally complicated and the properties are unknown. There is one exception. For AR, pure ARP processes, you can use the so-called Joule-Walker equations, where you estimate the autocorrelation function from lags 1 through p, like this, and then you solve this to get the phi 1 through p over here that are the partial autocorrelation functions. The function AR in R does exactly this, but you can see that it's not so different from just using the ARIMA function using maximum likelihood that I would generally recommend using. So this was a brief introduction to how to estimate things. My highlight is basically say maximum likelihood is the one thing to do by using one-step prediction errors. It coincides in many cases with the least square estimator, at least when you do the conditional maximum likelihood estimation. But also one thing to keep in mind when you start doing modeling is that essentially all models are wrong, but some are useful, which is also why my comment has been regarding when you're going to work with real data, it's about finding the least bad model. You won't find a perfect model, at least not when you have real data. It's typically not the case. So that was the first bit of this lecture. The next bit is going to R and then see if we can go through an example there. I will first simulate a model. We can see that it's an AR order 3 and moving average order 1. Then I will just set some plotting parameters. First say I just want one plotting window. I want the margins on the lower left, top and right to be 3, 3, 1 and 1. And then I want to move the text on the margins a little bit closer per default. So I get uses most of the space over here. So this is the data that I simulated. It's always good to just look at the data first, and then I will plot the autocorrelation function and the partial autocorrelation function of the data. And now the question is, which model is this? This is just what we kind of exercised during the last lecture. What you'll notice is there's an exponential thing here for the autocorrelation function, but there's also something going on down here that is not going very fast to 0 for the partial autocorrelation function. So a guess could be to have a model, say an ARMA 1,1 model, just to try something. And if you look at the fitted parameters here, it actually looks like the AR is not significant, but the moving average part is. We also estimate an intercept, but let's just do a diagnostic plot of what we have here. We see that after lag 3 there's still some dependence here, and we see that the autocorrelation function is not 0. And let's just plot the partial autocorrelation function as well. Well, again, this is also having some signal for lag 3 and 4, so we need to do something. Let's actually just go back and do the AR2 model just to increase the order of the AR by 1. See what happens. Not so much happened. We still have a similar structure, and by the same argument before, let's try to increase the AR. We could also have increased the moving average order, but in this case we kind of know what the reason was and what the data was, so let's go for the correct structure. But you should be aware of here that I used the structure where it's just the AR part that is different from the true order. The AR1 and AR2 estimates are insignificant, so it's not always easy to figure out what is actually true. And now when I go for the correct model order, I see that the AR1 is significant because the estimate is more than twice the standard error. Likewise for the AR2 and for the AR3 and the MA1. Again, we fitted a mean value that we should actually not fit, so we could refit it without that, but let's not just leave it there for now. I'll show that later. And look at a diagnostic plot instead. So we have the residuals up here, looks nice. The autocorrelation function, there's nothing, so that also means we don't have to look at the partial autocorrelation function. And the Young-Box test shows that there's no autocorrelation at any lag that is significant, because then they should be below 0.05. Now this object fit2 that we saved our model into, it actually contains a lot of different information. It contains the coefficients, sigma square, the log likelihood, the AIC, the residuals, and much more. So if we just take the likelihood, here's what's for the first model. If we do it for the second model, we have this, as is also given up here. Then we can just calculate the likelihood ratio test. It's described in the book. If you look at 2 times the difference in log likelihood, and there's one parameter different, and we want to look at the upper tail of the distribution. So what is the probability of being greater than? Then we see that that probability is slim to none at random, so the bigger model is the better model. We can also do an F-test where we look at the sum of squared residuals for fit 1 and for fit 2. We start with 4 parameters because we have 2 AR, 1 MA, and a mean value, and 5 for the other one, and then we can look up the F distribution for this. Now if we go back and redo this, where the one thing we change is that rather than including everything, we can also say we don't want to include a mean value. So we'll say false for this, refit it, do the same thing for the other one, just looking, seeing that actually the estimate for the other thing does not really change. The likelihood of course changes because we use a little bit less, but let's just go down and see the p-value is also invariant here because we remove two insignificant parameters in both models. Now the f-test, the sum of squared residuals are the same, but now we reduce both models by one parameter since we do not estimate the mean value any longer. And the p-value is again very, very small. So there's no doubt that we should use the ARMA 3,1 model as we did for the second fit here. And we saw from the TS-Dirac plots over here that we do adequately describe the correlation structure, so we are reasonably happy right now. What would be good to do now is to make an analysis of the residuals. How do they behave? I won't do it here, but I will do it later on. Also showed some examples of what to do in the previous lecture. So look at, you say, the QQ plot as well, maybe do a sign test, maybe look at a histogram and find the QQ plot more informative if you know how to read it. But right now I will move on to another example where I'll just take some data. First, let me just plot it. Look at the autocorrelation function and the partial autocorrelation function. So my initial thing when I look at this, it looks like something that is stationary at least. Also, it's confirmed by the autocorrelation function that goes reasonably fast to 0. There's no apparent structure up here, but when we look at this, well, first of all, we want to look at plotting some data and autocorrelation and partial autocorrelation function quite some time. So actually before starting to analyze this, let's make a function. We define a function by taking a model. We define a function of one variable in this case, and we make it do the exact same plot as we just made. So now we define the function and we can apply it. The only difference is that now I use dots rather than lines. We can just change that to say that the type up here should be lines. You can say lines has the benefit of being, it's clearer to see the individual points, but if you have something that is not changing very much, it's difficult to see the individual observations. In that case, the overlay option is good. Here will just be noise because here you have lines and points. But let's just go with lines for now. And now we have the same function again. Okay, so when looking at this, we have something here where up to lag 5 at least there's something in the ACF, maybe even further up. And the partial autocorrelation function will also have quite some structure here. And when you compare these two plots, you should also keep the scale in mind. The ACF always goes to +1, whereas the partial autocorrelation function, well, trims the y-axis so that you can see as much information as possible. So given that there is something happening here and something here, I suggest just using an ARMA 1,1 model, and I will exclude the mean value for this because you can see how nicely behaved it is around 0. So, and then you can specify which method to use, but you don't have to. Default is to do a conditional sum of squares, which is kind of the least square estimator at first, and then do a maximum likelihood estimation using that as initial guess, which is typically good. But this was just to mention, and you can experiment with that. The CSS option instead here will not give you a likelihood, so it won't have the AIC, but it's very much faster. So let's just look at the estimated parameters. We see that both are much greater in absolute value than twice the standard error. So it's not too bad. We can look at the AIC. We want to have the minimum of that or maximize the likelihood. If we look at our diagnostic tool for the residuals from this model, what we see here is, well, it still looks nice for the residuals up there. It's quite a long series, but we still have a lot of structure in the ACF and in the partial autocorrelation function. And it's the strongest signal is actually in lag 5. So let's just do the TS-Diag, which adds the Young-Box test, and we see that already from lag 2 there's something significant. Based on this here, you could be kind of encouraged to just say, well, let's just go for a order 5,5 AMA model. If we do that, now I'll just do it. I don't do that. First of all, it's a rather large model, so it, as you saw, just took a few seconds to do it. And if you look at the parameter values here, the AR1 model, the AR1 part is not significant because it's only about the same size as the standard error, the parameter value. And if you go through them one by one, 45 over 28 is not too. This is even smaller than the standard error, and again smaller than twice the standard error, smaller than the standard error, smaller than the standard error, and again a little bit larger than 1, but still insignificant. So all these parameters are insignificant. So it's not a good approach to just crank up and make a huge model. What is better is to go back and say, okay, let's look at the diagnostic plot that we have here and say, what could we look at? Where do we have some information here? We can see that there is something going on down here and also something here. So you might consider taking 2 steps at a time and say there is something exponential in both the ACF, it's hard to see what it is, and in the partial autocorrelation function. You could also say that that's mostly here and the ACF is simple, so let's start by just doing a moving average model. So here is one place, it's not clear which model to make as the next one, but let's just do an ARMA 1,2 model. We're back to a situation where all parameters are significant. The ACF is less than the 8,000 that we had before, so as such we're lucky. Let's just look at the structure here. It's not so much different from before, so we probably need to increase the order of the model once again. Now there's some indications that I would say that the partial autocorrelation function, even compensating for the scale, is exponential, and also there is a lot of things going on up here. Not so big, but there is some things going on up there. So I think just to speed up things a little bit, I will take 2 steps in one go here, and I look at the significance, and this is more than 4 times. This is very much more than 10 times standard error, and again much greater than the standard error, and much greater and much greater. So all parameters are significant. Now we get to a situation where we pretty much only have an exponential thing left down here. So I would say for now you have an exponential swing in the partial and not too much up here, but you actually see them also at the same lags up here. So it is actually difficult to say which model to make the next model. I will just pick one in this case. And we see that if it does get nicer, but again we still have some spikes out here. So this data set is actually not that well behaved as such. It's difficult to see. Maybe if I zoom in on the graph, it's easier to see what happens for the ACF here, you see something in like 4 and 5, but also in 7 and even in 9. So you can say that the tail here, there's information further out than what you see down here. You should ignore what is out there. So I would suggest increasing the AR part to say 4. And again checking, a quick check, all the standard errors are fairly small. And now if we zoom in on this, we actually get to a point where all the partial autocorrelation functions are inside, and also the ACF is well behaved. So now it's time to go back and look for the stereo autocorrelation, and it's also good. So an ARMA 4,3 is a good model describing this, at least from what we've seen so far. 7667, I guess that should also be, it is indeed smaller, quite a bit smaller than what we have up here, and the log likelihood was 3867, and it's also increased quite a bit down here. You should expect a change in 2. You can accept a change in 2 for adding the extra parameter. So skip this. On purpose I did not save that model into something. Remember that actually you only add 3 parameters here, but it makes everything insignificant. Okay, so let's look at different measures of diagnostics. First we could do a histogram, add a line where we use the d-norm, the density of the normal distribution that has the same standard error as the observed data, and it looks nice. You can change the number of bins if you like, but I prefer to look at the QQ plot, and adding the QQ line, you can see that it actually does look quite nice. We can also do kind of a time series plot just of the residuals, and if we want to have something nicer, we can simulate just to see if it is apparently, how would white noise look like. Here I just simulated some other white noise. There's some of you may have seen the so-called Wally plot, where you have to pick which one is the one that is different, or is the one in the middle different from the ones outside that are simulated. So one of the things that I covered you could do is a so-called sign test to test if every other residual has a new sign. So let's just, to make the code more readable, save the residuals in the vector called res, and the length of that is n.res. So the expected mean is 899.5, as in half the length minus 1, length minus 1 divided by 2, and the standard deviation of that you find here. So using the normal distribution, a 95% confidence interval for this is the following. I multiply with a vector of -1 and 1 to get the lower and upper bound of this. So if the true number, if the observed number of changes in sign is between 858 and 941, then we will not reject it. So let's check how many sign changes are there. What I do to figure that out is to take a product of all the observations, and actually I'll do this slightly different. I will remove the last one instead. If I index with this, so I take the product of everything but the first one and everything but the last one, and when I take the product of those two, if that is negative, then there's a change in sign. So I'll just sum how often did that happen? And 887 is indeed in that interval. You could also do a binomial test to see, well, 887 and n-res minus 1 chances, what does that give? That gives us a 95% confidence interval for the true value like this, and it does include 0.5, which means that we cannot reject that every other residual has a different sign. So everything here is fine. The test for the autocorrelation, in this case, we'll use up to like 15. That's similar to the Box-Cox test. You can also look into the function TS.Dirac to see how that works. If there's time at the end, I will do that. So first I will calculate the autocorrelation function of the residuals. I won't plot them, but what I will do is that I will take the autocorrelation function coefficient out, like this. Then I get these values out here, which are the same that if I just plot the autocorrelation function, those are the values that are from the second out to the 15th here. So the test statistic, if you remember from the previous lecture, is the sum of squared autocorrelation values times the number n. So that's test statistic, and we have to compare with a chi-square distribution with the number of autocorrelation function values that we are including minus the number of coefficients that we estimated. So it's 1 minus that. That's the risk of being more extreme by default. And in this case, we get 0.61. But a more efficient way, rather than doing 1 minus this, is to use the option lower tail equals false to just get directly the upper tail, which in this case gives the same. But if you get close to something that is, you can say, very significant, you may end up having a 0 if you do this calculation and you get actually something out down here. So this was the model that we have analyzed. We saw that the parameters are reasonably well behaved. Actually, we could test the MA3 parameter because it's not actually significant, but all the others are. So it would be at this point appropriate to actually go back and redo the whole thing. If I remove the, let me take this model, save it. Remove the MA3 model, oops, make it an MA2 model. We see here that the AIC was 7667 and now it's 7665, so it's lower, it's better. The likelihood was 3,825 and it's almost not changed. So that means when you can remove, if you can remove a model, a parameter, and the likelihood is about the same, then it's a better model. So we could go through the whole thing with this again. We won't see much of a difference. So I won't do it for now. But just to say, this is actually things that could have been a good thing to do up here. It would not have changed anything. It would just, because if you have a model that has too many parameters, generally the residuals will behave nice as well. So you can say those two things are orthogonal, but when you have a very small model, maybe we should just go through and then just do it. The easy way would be to just down here overwrite the model with the, that's not nice. Let's just do it for now. If we look at the QQ-plot and histograms, everything is fine. If we look at the data, it's fine. If we go for the sign test, well, it's the same number of observations, so the confidence interval is the same, and the observed number of changes is slightly different, but again, it's well within the interval. The binomial test, again, the interval here does contain 0.5, so we are happy. And for the autocorrelation test, let's look at it. We do calculate the test statistic. Before we got a p-value of 0.6, now we get 0.7, so it's even less significant, but still there's nothing further to investigate. So we actually end up with this model as being our best model. Now, if we do the cumulative periodigram of the raw data, we get something like this, and you can see that it's well outside the confidence bands given here. And if we do it for the residuals of our final model, actually it's well behaved. So we are in a point where this model, the ARMA 4.2 model, actually fulfills all our criteria. And just as a small add-on, one thing I like about R is that if you take a function and not apply anything to it, but just specify the function name, you get the definition of it. Now, this is one of those where actually what it does depends on the object that you get as input. So then you ask for which methods are there for the TS-diag function, and there is a method that is used for ARIMA. That is the one that we want to care about. TS-diag.ARIMA. That is the one that we want. It's not found because the stars marks that is masked. It's down in the namespace stats. So in order to find it, I need to go into the namespace stats and get the function definition in there. And here you can see the code that makes the tree plots. So the code for the Young-Box statistic is down here. Here's the plot, and the p-val are the ones that we care for. And here you can see how these are actually calculated. So if you are in doubt what actually goes on behind the scene, I think it's nice that you can go in and look at the code and see what actually goes on. But that was just a small add-on for those who, if you want to build your own functions, you can go in and you kind of grab those few lines down there and add that to your own analysis if you want to make life simple. So with that, I think I will say thanks for now and see you around. Bye bye.